In the last video, I introduced voltage as a potential energy difference that results from moving a charge from one point to another in an electric field. In this video, I'll talk about voltage as a fundamental parameter for circuit analysis. A lot of this video will be associated with terminology and sign conventions for voltages. Voltage is the energy level difference experienced by a charge when it's moved from one point to another in an electric field. Mathematically, it's dW by dQ. Units of voltage are volts, abbreviated as a capital V. Since the energy has units of joules and charge has units of coulombs, volts correspond to joules per coulomb. We care about voltage because it provides an energy difference that we can use to move charges around. Voltage has a magnitude, or a numerical value, and a sign. Voltages can be either positive or negative. The sign of the voltage is interpreted relative to a sign convention called the polarity. Since voltage is an energy difference between points, the polarity tells which point is assumed to have the higher energy level. This is indicated on circuit diagrams by a plus and a minus sign. The plus sign labels the point with the assumed higher polarity, and the minus sign indicates the point with the lower polarity. For example, I have a circuit element indicated by this gray box. It has two terminals that I have access to. If the voltage difference between the terminals is positive 5 volts, with the polarities indicated as shown, this means that this terminal is 5 volts higher than this terminal. Another way to interpret it is that the top terminal is 5 volts lower than the bottom terminal. Conversely, if the polarity is labeled like this, it means that this terminal has a positive 5 volt higher potential than this terminal. That means that this top terminal is 5 volts higher potential than the bottom terminal. Finally, I can have negative voltages. Here, the bottom terminal is negative 5 volts higher than the top terminal, which means it's actually 5 volts lower. So this voltage difference is exactly the same as this voltage difference. Simultaneously changing the polarity and the sign on the voltage has no effect. In summary, since voltages can be either positive or negative, an assigned polarity simply provides a sign convention by which we can interpret the voltages. Any voltage in a circuit has two components: a magnitude, or numerical value, which can be either positive or negative, and a polarity, or a sign convention, by which we can determine which terminal is actually at the higher voltage. If I reverse the polarity and also change the sign on the magnitude, the changes cancel out and the voltages are the same. So reversing the polarity of a voltage changes the sign on that voltage value. Notationally, polarity can also be indicated by subscripts on the voltage. The subscripts indicate the points between which the voltage is specified. The first subscript indicates the terminal having the assumed higher voltage, and the second subscript indicates the terminal with the assumed lower voltage. I'll do some examples and a demonstration next to illustrate this. Suppose I have a positive 7 volt potential difference between these two terminals with this polarity. This means that this point is 7 volts higher than this terminal. The same voltage difference can be indicated this way. The voltage difference is negative 7 volts, but that number is interpreted according to this polarity, in which the bottom terminal is assumed to have the higher voltage. So the lower terminal is negative 7 volts higher than the upper terminal. Now let's look at subscript notation. If I label this as terminal A and this as terminal B, I can represent this same voltage difference as VAB equals 7 volts. The first subscript tells me which terminal to assume has the higher potential. So VAB is specifying this polarity. VBA indicates this polarity. So if I specify this voltage as VBA, the voltage will be negative 7 volts. Changing the order of the subscripts reverses the assumed polarity and changes the sign on the voltage value. So VAB will always be the negative of VBA. This can also be illustrated with a quick measurement. I have a battery which should provide about a 9 volt difference between its terminals, with this terminal being the higher voltage. I can measure the voltage difference with this digital multimeter, or DMM. The DMM displays the voltage difference between its red and black terminals, with the red terminal being assumed to be the higher voltage. This corresponds to setting a sign convention on my measured voltage. Now, if I touch red to this battery terminal and black to this one, I read positive 9.7 volts, indicating that this terminal on the power supply is 9.7 volts higher than the other terminal. If I switch my multimeter probes, my measured voltage becomes negative 9.7 volts. I've switched the assumed polarity on my measurement and the sign on the voltage changed. Those two effects cancel out, which means that this terminal is 9.7 volts higher than this one. Voltages can be expressed relative to a reference point. The reference point specifies a point at which the voltage is taken to be 0 volts. Voltages specified relative to a reference appear to be the voltage at a point, but it's still a voltage difference between two different points in space. The reference point can be chosen as any arbitrary point in the circuit, or it can have a special meaning. Ground is a common reference point that's not arbitrary. There are several different types of ground, each of which has its own symbol. This is the symbol for earth ground, which is the voltage of the earth itself. Signal ground and chassis ground are alternate choices. Each of these has their own interpretation. The topic of ground is actually quite complex, but for this course, just assume that any of these symbols correspond to 0 volts. The concept of a reference voltage or ground is similar to measurement of altitudes relative to sea level. The elevation of Mount Everest is usually listed as about 29,000 feet. What this is really saying is that the difference in height between the peak of Everest and sea level is 29,000 feet. Using sea level as a reference is arbitrary. If we wanted, we could use the peak of Everest as our reference and say that the elevation of sea level is negative 29,000 feet. As long as everyone understands what we're using as our reference, we can use anything we want. Now let's look at a few examples. This circuit element has a 9-volt difference between its terminals with this polarity. We can choose one of these terminals as a reference and express the voltage at the other terminal relative to that reference. For example, let's choose node A as being at what we'll think of as 0 volts. Node B is 9 volts above the voltage at node A, so VB is equal to positive 9 volts. Our choice of reference voltage is arbitrary. I could choose node B as being 0 volts. Node A is 9 volts below the voltage at node B, so with this reference, VA is equal to negative 9 volts. Now let's ground node B. The voltage at ground is implicitly assumed as 0. So with the ground here, the voltage at A will be negative 9 volts, since node A is 9 volts below 0 volts. This case is slightly different than the previous arbitrary reference. If I have an earth ground at B, it's assumed I've physically connected terminal B to the earth, usually via a long copper bar hammered into the earth. On the other hand, I could ground node A. If I do this and measure VB relative to the ground, I'll get positive 9 volts. Node B is 9 volts above 0. Another way to represent the voltage at a terminal of an element is with an arrow. For example, this indicates that the voltage at the upper terminal of this element is VA and that the voltage at the lower terminal of the element is VB. The voltages VA and VB are always relative to some common reference. The reference voltage will always be indicated somewhere on the overall circuit schematic. For example, this indicates that the voltage at the upper terminal is positive 3 volts relative to some reference, and the voltage at the lower terminal is negative 2 volts relative to that same reference. That means that the voltage difference between these two terminals with the assumed positive polarity at the upper terminal is positive 5 volts, 3 volts minus a negative 2 volts. I won't use this representation for voltages very much in this course, but it's commonly used for elements that need an external power supply. Those are the basics of voltage as we will use it in this class. The important thing to remember is that voltage has an assigned polarity that provides a sign convention with which to interpret the numerical value of the voltage. The numerical value can be either positive or negative, and changing the assumed polarity changes the sign on that value. In the next video, I'll talk about the other parameter that quantifies electrical energy transfer, current. Current is simply the rate at which charge is passing some point in our circuit.